be going over some of my work as a graduate student at the University of Iowa and kind of an overview of my thesis as a whole. But before going into my work in particular, I'll provide a brief introduction to the Galactic Center region. And so this is, oh, can I advance the slides here? Yeah, there we go. So this is a radio image of the Galactic Center taken using Meerkat at 1 gigahertz. It's about a 2 degree by 1 degree field of view. And the Galactic Center is a unique region of the Milky Way with high densities and high magnetic field strengths. And it's also got a lot of interesting structures that researchers have studied for a number of years now. And I'll just highlight some of the features that are seen in the Galactic Center. So I've indicated this region of emission here, which is the Sagittarius A molecular region. And this contains the central black hole of the galaxy, Sagittarius A star. There are a few other molecular complexes like the Sagittarius B and C regions that are pretty much on the galactic plane, which is on this plane here. And then there are also these glowing thread-like structures that you can see pervade the galactic center. And these are what are known as the non-thermal filaments, which have been the focus of my research here at Iowa. And they're non-thermal filaments because they're emitting synchrotron radiation. And so some of the properties of these structures, actually, before I do that real quick, one of the prominent non-thermal filaments is what's known as the radio arc. It's a little hard to see in this image because it passes through this bright region here, but it passes through the galactic plane and is basically a set of multiple filaments here. But some of the general properties of the non-thermal filaments are that they have these extended total intensity features where they're far more long than they are wide. So they look like these glowing threads. They're highly polarized with percentage polarizations generally greater than 50%. And while they're continuous in total intensity, their polarized intensity is kind of this patchy or discontinuous appearance, although the polarized intensity does closely trace the total intensity, as you can see with these panels here. And there are some good review papers on like some of the properties of the NTF population that have been observed. Those are good for a review. Some studies for the NTFs have looked at a property known as the rotation measure. And so since the non-thermal filaments are polarized, you can extract information regarding the magnetic field local to these sources. And one way to do that is to get this parameter that's known as the rotation measure, which you obtain by plotting the polarization angle as a function of wavelength squared. And you find the slope of the best fit line to that, and that's the rotation measure here. So for this particular NTF, the rotation measures are like, negative 1,500, negative 2,000 radians per meter squared, which is quite an extreme rotation measure compared to a lot of other cosmic sources, but all the NTFs studied in this way have rotation measures of about the same magnitude. And so using the rotation measure, you can get what's known as the intrinsic magnetic field. So this is the orientation of the magnetic field in the plane of the sky as emitted at the source of the emission. So in this case, at the location of the non-thermal filament. And so this figure here shows with these black dashed lines the orientation of the magnetic field, and it's found to be generally parallel to the extent of the NTF's total intensity. And other NTFs that have been studied in this way have seen or have this same kind of feature of like a parallel magnetic field or a magnetic field that traces the non-thermal filaments. And so if we look again at the distribution of NTFs in the GC, like in this image, you can see that a lot of the NTFs are oriented roughly perpendicular to the galactic plane. And that's led a number of researchers to conclude that there might be this pervasive magnetic field that's oriented perpendicular to the galactic plane in the galactic center region. but it's not as clear cut as that. If you look at dust polarization observations in like the molecular cloud regions on the galactic plane in the galactic center, the magnetic field there is found to be parallel to the galactic disk rather than perpendicular, as is seen in the non-thermal filaments. And it's unclear how these two different field systems interact in the galactic center. And then some other work that's been done more recently. This is from a 2019 Nature paper, again using Meerkat. They found this large scale like radio bubble, which extends vertically above and below the galactic plane. And this bubble encompasses a lot of the NTFs seen in the galactic center. And the bubble is also this large synchrotron source. And so it's possible that this bubble is indicating an energy transfer from the galactic plane or galactic center into higher and lower latitudes. And the bubble could also be inducing the formation of the NTFs, although a lot of that is still kind of unclear whether that's in fact the case. And then kind of another complicating factor of this non-thermal filament population is that there seem to be two different kind of sets of NTFs in the galactic center. So like the radio arc, for example, consists of a number of individual filaments. And then there are also structures like these that I've indicated and a few more in northern latitudes where they seem to consist of 6 or more individual filaments kind of closely packed. And then there are these other filaments here, like the snake here, where it's just like a single strand or maybe 2 or 3 strands, but that are more like bright and not as close together. And so it's unclear how these structures, whether they're all part of the same population of structures or whether they were formed in different ways or what the relationship is between these different populations of NTFs. And so the first question of my work at Iowa was to look at the radio arc, which is a prominent structure of several NTFs, to see how the properties of this structure compare with some of the other NTFs that have been observed. And a lot of the previously observed NTFs are those kind of single strand NTFs in that other population. And so to address that question, I used a VLA data set that covered 3 different frequency bands and a number of different arrays. So the VLA is an interferometer, unlike Green Bank. And so the different arrays here give us sensitivity to different source sizes, so to large and small scale structure. Our resolution here is generally on arc second scales, and then the frequency range provided by these different bands allows us to study the radio arc from 2 to 12 gigahertz. Although one thing I want to note here is that this frequency range, it's not a contiguous coverage through that frequency range. There are frequency gaps between each of these bands once you account for edge channels. And so these are our pointings for those different bands over the radio arc here. And then just to show some of our results from this study. So our total intensity here at lower frequencies reveals how much of a complex region the radio arc is embedded within. We see well more than 10 individual filaments that make up the radio arc. There are also these 2 H2 regions and a lot of other structure making up this image. I won't go into too much detail on this image yet, just due to lack of time. We'll be revisiting some of the structures we see in this image later. And then if we compare that with our total intensity results with some of the previously published work that was done a few decades ago on the structure, we see that we reproduce the key structures here with good fidelity, but we also have a better sensitivity than has been seen before. So if we look at the polarized intensity that we obtain for the radio arc, we find that significant polarization is only seen within this region of the radio arc. and it doesn't extend further south or north in the arc NTFs beyond this region. But within that region, we see that it's a fairly continuous polarized intensity distribution, but we also see these regions of polarized intensity that extend into regions of low total intensity, and these I've marked with the black arrows here. And these kinds of regions of polarized intensity are unexpected, because if we look back at, say, this NTF example I showed earlier, in this NTF and in the other NTFs studied previously, the polarized intensity has only traced the total intensity. And so these kind of extensions we're seeing with the black arrows are unusual, and we'll be revisiting these later to help with some of our other conclusions later on in the talk. So then we produced the rotation measure distribution for the radio arc. And so some work had been done on the radio arc before on total intensity and polarized intensity, but there hadn't been a map of rotation measure produced for the radio arc before this work. And so to do that, we just fit our polarization angle as a function of wavelength squared. And the slope of these lines here is the rotation measure for each line of sight. So I'm just showing some examples of these fits here. And our total distribution is this color scale image here, where the units are in radians per meter squared. And so these kind of rotation measure values are, again, extreme compared to other cosmic sources, but they're in agreement with what's seen towards other NTFs. And there's a generally lower rotation measure magnitude seen in the center of this distribution. So then using this rotation measure, we can extract the intrinsic magnetic field distribution for the radio arc. And what's interesting, so that's what I show here. And what's interesting about this distribution is we have regions of parallel magnetic field, which we would expect to see from what we've seen in other non-thermal filaments. But we also have these regions of rotated magnetic field, which are not seen in the other NTFs. And if I overlay some region markings to help show this, you can see that it's the rectangular regions mark parallel magnetic field zones, and the elliptical regions mark rotated magnetic field zones. And there's a fairly regular alternating pattern here that we see for the intrinsic magnetic field. And if we see where the elongated polarized intensity features fall in relation with this magnetic field distribution, we see that they generally occur at transition points between like a parallel and a rotated region generally. And so these elongated polarized intensity regions and the rotated magnetic fields both are unexpected properties. We didn't expect to see that for our results for the radio arc. So we were scratching our heads for some time trying to figure out like what could be causing these features we're seeing. And we ended up turning back to our total intensity distribution. This is the same one I showed earlier, because what we noticed is there's this large bubble, it seems, that surrounds the radio arc, or at least the observed portion of the radio arc. And there are also these total intensity features that seem to connect from the bubble to the arc NTF. So there's this one and this one here. And they also connect to the arc NTFs at the points where we obtain our polarized intensity emission. So we were interested in overlaying, like, we were wondering if these features cross in front of the arc NTFs, and if so, how they would cross over the distributions we showed before of like the rotation measure and magnetic field. So that's what I'm showing in this figure here, where this eastern projection is the extension of this feature over the arc NTFs. And then this western projection is the extension of this feature over the arc NTFs. And what we see is that the eastern projection coincides with a region of parallel magnetic field, whereas the western projection generally coincides with a region of rotated magnetic field. And they also roughly coincide with these elongated polarized intensity features as well. And then if we see how these projections relate to the rotation measure and polarized intensity, we see that the eastern projection coincides with like peak rotation measure magnitudes. And the black contours here are polarized intensity, so it coincides with generally lower polarized intensity. Whereas the Western projection coincides with like the opposite behavior of the data. So generally lower rotation measure magnitudes and peak polarized intensity. And so these projections caused us to think that there might be a relationship between these total intensity features we're seeing and some of the behaviors we're seeing in our other data sets, like the polarized intensity. And so we were thinking about what could be like a model that explains this kind of effect. And we developed a preliminary model in this work to kind of explain some of the results we obtained. And so our model is based on this radio shell. And then we are treating these total intensity features that bridge the shell and arc NTFs as basically density enhancements on that shell. So we're assuming that the shell envelops the radio arc in all directions and that these are density enhancements coming kind of in front of the radio arc. And so this is like a sketch of that model here, where our radio shell is this kind of large circle, the arc NTFs are these black lines, and we have these density enhancements which correspond with these total intensity features. And we're thinking that since the different density enhancements have different effects on our data, that they're probably not both foreground to the radio arc, and only one of the two that we see here is in front of the radio arc and the other comes behind the radio arc. But a lot of this was kind of, a lot of this is preliminary because our VLA data set didn't allow us to do a more comprehensive like analysis of the rotation measure properties of the radio arc. And so this was as far as we were able to develop this kind of theory in this paper. So what I've been doing since the publication of that work has been following up on the VLA data set with a Australia telescope compact array data set that is contiguous in frequency. And that will allow us to probe in more detail some of the rotation measure and depolarization mechanisms we're seeing and try and analyze quantitatively some of the effects that are going on local to the radio arc. And that will hopefully verify or disprove the model we were proposing in our 2019 work. And so the properties of this data set, we have these four ATCA frequency bands. The different arrays here, again, give us sensitivity to different source sizes, large and small scale source sizes. The ATCA data set has a little lower or poorer resolution than our VLA data set, but not by much. And then our frequency range is a little more limited, 4 to 12 gigahertz instead of 2 to 12 gigahertz. But the advantage here is that it is contiguous. We don't have any frequency gaps in that 4 to 12 gigahertz range. And so our pointings here, for these bands, the red circles actually correspond to the pointings. The purple circles correspond to a lower frequency pointing that we ended up not being able to use due to quite a lot of RFI. So just to show some of the 2D distributions we have from the radio arc. So these are like distributions at particular slices in frequency, just to showcase our data. So our total intensity at about like 6.5 gigahertz reproduces a lot of the features we saw in our VLA data. We see the same filamentation of the radio arc. We see these same like density enhancements of the radio shell approaching the radio arc at the same locations. And the field of view is a little more confined, but we do see evidence of the radio shell in this image as well. And then if we look at the polarized intensity, we've like in our VLA data, we find that the polarized intensity is confined within a narrow region of the radio arc, the same region we saw in our VLA study. We again see these polarized, like elongated polarized intensity features. And our lower frequency data is quite sparse in polarized intensity, but at higher frequencies, we see a lot more polarized intensity and more of these elongated polarized features. And this agrees with what we saw in our VLA data. In our VLA data, the radio arc had more polarization as we increased in frequency as well. And so we're confident that our ATCA data reproduces what we were seeing with the VLA. And so the key with this data set now, like what we want to do with it, is we want to run a technique that's known as QU fitting on our linear polarization. So that's the Stokes Q and U data as a function of wavelength squared. And so what that allows us to do is you can create a model or models of different depolarization and rotation mechanisms. So like a simple Faraday screen, for example, and fit that as a function of frequency. Determine the best fit to your data using the model, using Bayesian methods, and see if it's actually an accurate description of what you're seeing in your data. And you can use that for different mechanisms to see which mechanism best explains what you're seeing in your data. And what's nice about this technique as well is that if you're thinking you have multiple different media that are causing effects in your data, you can model each of those media individually and simultaneously to see if what number of components is causing the effects you observe. And that's a huge advantage over what we were able to do with our 2019 data, because with those linear fits we were doing with the polarization as a function or polarization angle as a function of wavelength squared, there wasn't much we could do to assess what exact mechanisms were causing the rotation we were seeing. And so some of the basic models we're considering are that we expect there to be external screens. So these would be media between us and the radio arc that are causing rotation of the radio arc's emission. And so one effect we're considering is this one known as external Faraday dispersion. And this is kind of the equation characterizing that effect. So we would make a model using this equation. And this is just caused by a foreground screen that has a varying magnetic field within it. And this is kind of just a basic diagram explaining like what that effect would look like for a single line of sight, where you have your polarized emission coming in at some initial angle, and then as it passes through this magnetized medium, it becomes rotated, and its final angle is offset from what its initial angle was. So this is kind of one of the external effects we're considering. And then we have some internal Faraday effects we're considering as well for this data. So we don't expect a significant amount of internal Faraday effects from the radio arc itself, but for that radio shell model that we proposed in the 2019 data, there might be internal Faraday rotation there because we don't know much about what could be going on in that medium. And so we have these two different internal Faraday effects here that we've created models for that we're also analyzing. And so what we've done so far is we've fit single media models to our radio arc data just to see how well a single screen can match what we're seeing in our distributions. And so this is an example of like the output corner plot once you run the Bayesian analysis. And what we're seeing here is that the best fit result is found at the peak of the various distributions, the different parameters you feed in. And that's what we would expect to see for like the best fit result of a given model. So that's a good sign. And this example is done just assuming a single external screen with this Faraday dispersion mechanism that I showed earlier. When we look at the resulting model fit, though, of this best fit result, we see that it doesn't fit very well. So the actual lines with error bars that are kind of hard to see here is the data as a function of wavelength squared for our ATCA results. And then the solid lines are the resulting best fit model. And we can see that there are a number of areas where the model doesn't line up with the data at all. And you can also see that in the Stokes Q versus Stokes U plot, the solid line model fit to this data doesn't reproduce what we're seeing in the Stokes Q and U data at all. And if we've done this kind of analysis on a number of single media models at this point, and they all show the same kind of result where the best fit is drawn from the peak of the distributions, the parameter space distributions, but the actual model doesn't reproduce the data well at all. So what that indicates is that we need to look at models involving multiple different screens that could be causing effects in our data. And so that's where I've basically gotten to with this work at this stage is I'm starting to test these multiple component models now in using QU fitting. And so some examples of those multiple component models, like this is one that just involves some number of external screens. For this example, I'm showing 3 external screens that are between us and the radio arc, and each of these screens is causing its own amount of rotation to the emission. And so this is kind of one model I'm considering, and just naively, I would expect this kind of model to fit well in regions where we don't expect the radio shell to be a significant factor. So these would be regions where we're getting parallel magnetic field from that 2019 magnetic field distribution. And then this other model I'm looking at involves, again, some number of external screens, but also a internal medium which characterizes the radio shell itself. And that would either be using that DFR or IFD mechanism. And so for this, I would expect it to be a more successful fit in regions where we have the rotated magnetic field, because those are the regions we expect the radio shell to be a significant medium in terms of explaining the effects we see. And so the goal of all of this is that what we should see at the end of the day is that the regions of rotated magnetic field are fit with a different kind of model than what we see for the regions of parallel magnetic field. And that will allow us to quantify the properties of this additional intervening medium that we've called the radio shell for now. And so that's still TBD because this is still a work in progress. So then the other kind of work I've been pursuing since the 2019 data has been to compare how other filaments like the radio arc, other like filaments containing like 6 or more individual filaments, how those compare with the single thread NTFs. And so if we look back at this meerkat image of the galactic center, we've got the radio arc, but we've also got a number of other filament clusters as well, like this one here, a few in the north. And so what I've done is I've gotten some VLA data of 3 of these other NTF systems. So one of this system here, one of the system here, and then one of like the southern portion of the radio arc, because our previous 2019 radio arc data is up here closer to the galactic plane. And what we're planning to do here is compare the properties of these NTFs with what we've already seen with the radio arc, and then also compare to the isolated threads and see what kind of statistical results we can obtain. And so we've already done the total intensity calibration and a lot of the total intensity imaging. So I'll just really quickly in my last little bit of time here show some of the preliminary total intensity images we're getting from this new VLA data. So this is of that first NTF cluster here, comes through pretty strongly. This is of the southern portion of the radio arc, and you can actually see that this looks like it overlaps with some of the data from our 2019 work. So we'll probably combine this data set with our 2019 data to make a super data set of the radio arc. And then this is of the third NTF cluster, which I think there's a bit more imaging work needed here to bring out these fainter NTFs more strongly. But this is also a work in progress here. So with that, I will show up my conclusion slide and take any questions.
Thank you, Dylan. So I had one question. On the density features that you showed a couple slides back, the ones that you were saying were, I guess, alternating with the NTF thermal filaments. Yeah.
I mean, these kinds of things, yeah.
So are you arguing that those are two independent structures that are just like projected along the same line of sight, or are you saying that those are two density features are part of the same structure?
Yeah, so we're thinking that the radio shell and these density enhancements are all part of the same structure, yeah. So these would be density enhancements of that radio shell.
All right, so it looks like we have a question from Allie.
Nice talk, Dylan. I have a question about, well, it's in the QU modeling. Normally, you have to account for the spectral index, and there's a variety of ways that you can do that. So I'm assuming based on the labels, I know that particular image is from Sullivan et al.
Yeah.
But maybe just tell me like what your approach was to handling the spectral index with this data.
So what we're doing, I think this answers your question. So what we've done is we've divided the Q and U data by a model of the total intensity. And so this is like the Q over I, U over I data as a function of wavelength squared. And then that is producing this polarized intensity data here. And so I think that's what you mean by accounting for the spectral index, is we basically divide out a model of the total intensity before doing any of the fitting we do.
Yeah, that's exactly what I'm asking.
Yeah.
Thanks.
Yeah.
All right, it looks like we have another question from Namir.
Yeah, hello, can you hear me?
Yep.
Yeah, that was a very interesting talk. Dylan, if you could just put up one of the slides which just shows the radio bubble, I guess you call it, or something.
Oh, yeah.
I mean, did I?
Yeah,
so maybe I just missed it, but did you say anything about the continuum spectrum of that shell? I mean, is that an H2 bubble? Is it a supernova remnant bubble? What is that thing?
Right, yeah, so I didn't really talk about that. I completely forgot. So there has been some previous work that has shown this feature around the radio arc. I want to say it's like Simpson et al. 2007 or maybe 2009 that show this feature in, I believe it's the submillimeter. And what they think it is that this bubble is actually centered on a star cluster known as the quintuplet star cluster. And they think that this shell is a shock front of outflowing winds from that star cluster. And as for the specific properties of the radio shell, I'm drawing a blank on that, like, you know, density and kind of spectral index kind of stuff. I'd have to refer to the literature again to look at that.
Right, so from what you said, I'm guessing it's thermal, but that would be interesting to, then again, if it's a shock, anyway, that'd be interesting to just know. Anyway, that's yeah, it's pretty neat. Thank you.
Yeah, no problem.
All right, looks like we have a question from Loretto.
Hi, Dylan, great work. I don't know if you mentioned it, but also related to spectral index, what is the spectral index you're getting from the filament?
Yeah, so the radio arc has a pretty flat spectral index of like negative 0.2 or so. A lot of the other filaments are steeper spectral indices of like negative 0.7 or so.
Mhm.
Yeah.
All right, any other questions for Dylan?
Could I ask one more follow-up?
Go ahead.
I know that this is, again, sort of motivated by the last question. There have been some studies that have shown gradients in the spectral index along the filaments. Is that anything that you've noticed? Or like when you said minus 0.2, is it just like rock solid minus 0.2 along the whole thing? Do you know?
Yeah, so we've done a little bit of work on the spectral index overall, but we haven't done like an in-depth analysis. So one of the goals of this last work here is to do some of that follow-up work with the radio arc's total intensity as well. So we're thinking with these VLA data we've gotten that we'll probably release 2 papers, one on the total intensity properties of these 3 pointings, as well as our previous 2019 results. Because what ended up happening in our 2019 data is we saw these total intensity features and behaviors that were really interesting, but the paper was already getting too long. So what we're going to do is we're going to add a lot more discussion on the total intensity, and we're going to do some of that work, like you were saying, of looking into spectral index gradients along these filaments. And so that will be something we'll publish later. And then another paper on this work will be looking at like the polarized intensity and rotation measure characteristics of these new regions.
Thank you.
Yeah.
All right, any other questions for Dylan? All right, well, I think we will end here. Our speaker next week is going to be John Ramsey from the University of Virginia, and he's going to tell us about simulating the growth of small planets via pebble accretion. So we'll see you all next week.
Thank you guys for attending.